Alright, hey everyone, welcome back to 3 Deviations. In today's video, we want to talk about surface area. So we talked about arc length in the last video, and that allowed us to find a length of a curve. So if I have a curve like that, I can find the length from here to there. And it was pretty helpful because we can now use integrals to find areas, volumes, and lengths of continuous curves, which is pretty cool. Now, as I said earlier, this unit's going to be short and sweet, so we're only going to really be spending one video on this topic because it's fairly straightforward. It's really a continuation of the disc and shell method that we talked about in Unit 5. We really slowed down at the beginning of Calculus 2 to talk about applications of integration and techniques of integration, but now that we know those, we can speed back up again and start going a little faster through calculus. All right, so without further ado, let's talk about surface area. So let's talk about the definition. So to find the surface area by rotating f of x about the x-axis on AB, and just so you know, this goes for the y-axis as well, just by changing some differentials around, on an interval between a and b, the surface area is going to be equal to the integral between a and b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. So what can you see here? So you can really see that this is 2 pi times f of x multiplied by the arc length kind of square root thing that we get with the integral there. And we can simplify this as well. We can rewrite this guy here. We can rewrite that as ds. So let's set 1 plus the square root of 1 plus f prime of x squared dx equal to ds. You're going to see that a lot in multivariable calculus where you're going to change differentials around and you're going to have differential analysis, and you're really just going to be putting in differentials as stand-ins for expressions plus a differential tacked on at the end. So again, setting the square root of 1 plus f prime of x squared dx equal to ds. Okay, so this seems pretty straightforward. If we have a function, we want to find the surface area of that function, we use that formula to find it, right? So that's similar to the disc and shell method. You can use area between curves to do this, or what have you. There are going to be a lot of different situations, as you will see on our problem set. Okay, so here's an example that we'll do. So I want us to rotate the square root of 9 minus x squared about the x-axis and find the surface area between -1, x, and 1. All right, so let's see. So there's our rudimentary coordinate plane. So as you know, this is going to be part of a circle. So let's see. I've got a circle here. So it's going to be a circle of radius 3. And we're rotating this about the x-axis. So we're going to end up getting a sphere, but we're only on -1 to 1. So we're going to be getting kind of a little, we're going to be getting like a little bit of a sphere. Be getting a little bit. So we're going to be getting like that little napkin ring. We want to find the surface area of this napkin ring. So we want to find this area here. All right, so if we remember our formula, we're going to want to find some things first about our function. So first we want to find the derivative of our function. So to find the derivative, we need to use the chain rule. So we have the inside function inside the square root operator, and we can find the derivative of that, and then that goes on top of the derivative of the outside function. So we end up getting -x over the square root of 9 minus x squared. All right, but now we want to find the square root of 1 plus f prime of x squared, because that's what goes inside of our integral, part of what goes inside of our integral. And that is equal to the square root of 1 plus x squared over 9 minus x squared. Okay, this looks pretty hairy to be putting inside of an integral, but it's going to turn out all right because we've still got to put this function inside of the integral as well. So let's do that. So the surface area is going to be equal to 2 pi, we can pull that outside the integral, times the integral between -1 and 1, times the square root, times our function, of 9 minus x squared, times the square root of 1 plus x squared over 9 minus x squared dx. Now we can combine these fractions and simplify a little bit inside of the square root. This gives us 2 pi times the integral between -1 and 1 of the square root of 9 minus x squared times the square root of 9 over 9 minus x squared dx. All right, simplifying further, we're going to get the integral, sorry, this is wrong. Get 3 there, and a 9 there. So you get 2 pi times the integral between -1 and 1 of the integral of the square root of 9 minus x squared times 3 over the square root of 9 minus x squared dx. All right, so now what we can do is we can simplify things. These are going to cross out, right? And now we've got that 3, so we've got 6 pi. Got 6 pi, because we're multiplying that 3 out. And then we're just left with the integral over dx. So we've got the integral, or sorry, then we've got 6 pi times -1 plus 1, so 2, so then we get 12 pi. So 12 pi is the value of our surface area here. Sorry for that little mistake there. Sometimes this is probably the unit I'm most prone to mistakes on these PowerPoints, just because there's so many moving pieces. All right, well, anyways, thanks for watching this video. In the next one, we're going to be talking about some direct applications of integration, like applications to physics. Maybe we'll spend a couple more videos over there. And then we're going to be moving on to differential equations. As I said, this is a short and sweet unit. Check out our problem set on the surface area, surface of revolution in Unit 7. All right, thanks for watching. See you in the next one. Bye.